Hello, welcome to my talk. We started 3 years ago to implement a language or a system that tries to emulate Scratch on the phone, with the idea that you don't need, when you use this app, any PC. You can do the whole development cycle on the phone or on a tablet. Initially, we started with, it works, I think. Yeah. Initially, we started with Android. That's why we made this kind of symbol. It's a Scratch cat. It's a Scratch cat that is transformed into an Android robot mascot. And since last year, we are also on iPhones and Windows phones, and also develop now an HTML5 version. I think the best way to show you this is by simply showing you how it looks like on the phone. So here, you see the screen of my phone. This program, the system, the app is now called Pocket Code, because initially we had the name Catroid, but that's too Android specific, so we decided to rename it. And one of the names was Catroid, and okay, it will of course not work the first time, but yeah, now it works. And I want to show you a few of the programs that can be made directly on the phone without any PC needed. So in order to show you the capabilities, I will show you several programs. This one is a program that I made on the phone completely. It's a little bit a bigger one. There should be also sound. Maybe, okay. No, it doesn't work with the sound. Okay. Anyway, it's possible to fly around like this with using the sensors, and you can also shoot and such things. Yeah. So this is all developed in a programming language that very much resembles Scratch. Also structurally, you have the background, you have the objects. In each object, you have scripts, looks, and sounds. For instance, here for the airplane, I have the look, and we also have an editor that allows to zoom in up to pixel level to make parts of the picture transparent. That was very important for us, because most apps that allow image manipulation on phones don't have this capability. They don't need to edit pixels. They don't need to make something transparent. We needed that. So this editor is fairly complex. It has all kind of, things, and all kind of tools, and we developed it also ourselves. So now I go back and I show you a little bit the scripts. So the idea here is that it's possible to program using just your thumb. You just need one finger. So here, if you tap on the plus in the lower left, you see the categories of different bricks. And for instance, if you go on the control brick, you see all typical bricks or variables, looks, and so on. We also have sensors, as you have seen, the inclination sensors. I steered the airplane just by moving around this plane, the phone. And some things are still in the works. We just went into the Google App Store 2 weeks ago with a beta version. Maybe I have to say this is also a free open source project. There are people from 20 nations working together with us. We are based mainly in Austria, but many people are also from around the world. We have versions in Japanese, in Korean, in Chinese, in Russian, and so on. And it's really very much inspired by Scratch. For instance, we also have our own sharing site where it's possible to upload and download programs with remixing and everything included, like very much like in Scratch, but we are by far not yet as advanced as Scratch. So for instance, what we are still missing is kids cannot yet comment on each other's projects. That's something we'll still have to add. But already now, we register all the remixing information so that later we'll be able to show that. So, connection, yeah. So I show you another program here. For instance, this tic-tac-toe master is just a small implementation, but again, fully implemented on the phone. Here, all the different objects, and it looks like this. Now I can decide that the computer should start, and I can try to, well, I will lose in this case. So, one more small example is I want to show you how to make a new program. So I will now just first enter the name. I make, because it's kind of nice, always this, those who have heard the talk know this already, compass example, because it's very easy to program. So I leave the background as it is. I make a new object that I call needle, which should be the needle of the compass. So what I need is a costume, or look, as we call them. I draw a new one. It's just, you know, like this. Then I crop it a bit. Wouldn't be necessary, strictly speaking, but yeah, it makes it a little bit smaller. And then I have this as an image. I could, of course, rename it, but let's make that quickly. So I'll add first this look, and then I'll need a loop, which is a forever loop. And basically what happens is that the needle should always turn in the direction. The directions are defined in the same way as in Scratch, so nothing new here. What is new is that we don't have bricks for formulas. We were thinking a lot of, really a long time, how to solve the problem that the screen is so narrow. And on some day after jogging, I found, well, why don't we use this metaphor of a pocket calculator? Everyone is used to them, and everyone has learned in school how to write formulas on paper with parentheses and so on. So it's not such a big deal to use normal formulas. So here, when I press on math, for instance, I have all the math functions. Under object, it's a little bit the connection. Sorry, this is a live demo, so it's always a little bit dangerous that it doesn't work. Came out here, yeah? So here I have like transparency, brightness, size, direction, and so on. And here I have the sensors. So far we have implemented 6. So I enter here this compass direction. Of course I could do some more complex formulas. If there is a mistake here and I go back, it will just highlight to me where the problem was. So here in this case, I don't need all of this. And just go back and execute that, and that's a compass. Yeah? So it's quite possible to develop on such a small device. The next interesting thing is once a kid now uploads this to our sharing website, another kid who has an iPhone or a Windows phone or a Firefox OS phone, once they come out, will be able to download exactly the same program and run it directly on his or her phone. So that's, I think this cross-compatibility is also very interesting. That's why we also decided not to call it Catroid, but Pocket Code, because this version will be called, this app will be called Pocket Code on all platforms. We're really platform independent here, and we don't want to have to tell kids, no, you have a different version, you cannot exchange it. Yeah, so just the name should be enough. iOS is a long story. Maybe afterwards I tell you more about it. Yeah. So one more thing that I want to show you. It's a huge project with many people participating, and there are many sub-projects. The version that I just showed you is the version that will be very soon in the market. The Paint program that I showed you is an independent program. Actually, it can be used independently, and that one is already in the market since for 2 weeks now. So we have many other versions. For instance, this one here, that's not still with the old interface, which is much more colorful and, well, not as well designed. Here, for instance, I have, but internally it looks very much the same structure. Here, for instance, we have bricks, like this. And if I execute that, that's an interesting variant where we have a physics engine included. So programming the ball is very simple. So you see, this is really something that is working very easily. And I can play such game. And each time I press on this Lego brick, it will become a bit bigger. And, oops, I went out too far. If I look at the code for this, you'll see when tapped, at the bottom, when tapped, broadcast restart ball, change size by 20, and here we still called it ghost effect. Later we changed that to transparency, but here it's still ghost effect. So, oops, didn't want to have this. So here is the pluses on the top. Change ghost effect, yeah, that's what I wanted to show. So when I execute it now, and each time I touch the brick, it will become a little bit more transparent. So you see here how this works with the programming. Of course, here we need a few additional bricks. Like if you look, the brick that is now at the top, turn left 145 degrees per second. Yeah, so it's turning all the time. For instance, that's one. Or here, when project starts, it's a fixed physical object, this brick, meaning that it's not subject to gravity, for instance. So, yep. I think it's because I have to turn this off. Okay, so now, yeah, basically what we already have is support for Lego robots for the Mindstorms, but recently we tried also something new. We have this small robot. Last year at the Scratch conference in Boston, there was a group of Korean scientists who presented this robot, and they asked us to allow it to be programmed through Catrobat. And the interesting point here is that it's possible to put the phone into its front like this, and it also has some interesting sensors like distance sensors and so on. So communication is via Bluetooth. I'll try to demo that live now. Let's see if it works. Sometimes it doesn't work because there are too many Bluetooth connections in the room, but let's see. So I have to go to the, I can also display this. So here, this robot is called Albert, and now I'll try to control it. Yes. So here, you see, for instance, I can control the eyes or move it. And there at the bottom, you see here also the distance sensor. So depending on the distance, you can, like find out whether it's going to bump into something, and it's possible, well, to control basically to control the robot. This is just an example program that we did to test all the functionality. Like here, for instance, it just says Albert move motor with a certain speed and so on. Yeah, it looks very similar to the Lego bricks actually. So another project, oh, maybe. We try also to connect to different hardware. For instance, we have one such project that allows us to control Bluetooth Arduino boards, which is also very interesting to control any kind of robot and any kind of application. But we have also interest in other robots like this one, which is very cute and interesting for smaller kids. For the larger kids, we have the following. This is a drone that can be also controlled through the phone, and I want to show that also live. Last time at the MIT it didn't work because there were too many Wi-Fi connections. Test it. I'll try it now again. Yeah. So let's see. It's not totally trivial to do it, but let's try. So if any one of you has this app for the drone, please don't turn it on now, otherwise I'll not be able to connect.
It doesn't allow multiple connections.
No, not the drone, because, yeah, but the drone, should be controlled only through one thing. Why doesn't this work again? Yeah, no? Okay, I have to hold it. And it's connected to the drone, and it's also a different one here, drone. So let me just see, I think the last project I made just starts the video. Okay, and I'll make it also a little bit bigger because it's small. So it will just like for 5 seconds yeah, it's a little bit dangerous. So. Oops, it's again not working. Now this is not good. Can't believe. Yeah. So here, I don't know. I try to restart it. Oh, but you see, yeah, it works. Yeah. So I'm not sure if I should let it fly also. Okay. I try to. Yeah. Yeah, you're safe. So what I can do, for instance, is to let it just fly up and then go down again, we have all those. It's a little bit shaky here with this connection. What is happening? Sorry about this. Does it work or not? Yeah, okay. Here. Okay, anyway, I will insert the brick that makes it take off, and then another one that makes it land after this, these 5 seconds. So let's see whether it works. Quite fun, huh? Oof. I'm so happy that it worked again. 3 minutes left. Yeah, I can say the project really is huge. We have more than 200 contributors. We have extensions for NFC. We have an extension where it's possible to sing into the mic, and it will transpose that into musical notation. Because we don't just want to foster creativity in terms of software development, but in general. So music is also very important. I'm from Austria. Wolfgang is my first name, Wolfgang Amadeus Mozart. You know. This is also important for us. We have a gamepad expansion. And what I actually announced this talk in when I submitted it is we have now, as a newest addition, a translator from Scratch projects to Catrobat projects. So I show you quickly, and I hope the sound works. I hope the sound works very quickly. A nice program from the Scratch website. The sound is here. Let's see if this works. So.
I got my sights set on you, and I'm ready to wait.
So basically, this was a program I think that was made by a Scratch user several years ago called Tüster. It was very nice. I use it always as an example. And with our Scratch to Catrobat converter, where I don't want to display the address now because it's not yet finished, we can translate this program as it is into a Catrobat program, and I want to show that too. So we didn't change anything here when we developed that. Still have a few seconds. Oops. So, go back. So, yeah, must be here. And those are all the downloaded programs. So here, for instance, this is the Hannah Montana without any changes. So it does the same thing. The music is also there. I try to add that too. Yeah. So there are still some glitches like this white line on top. And yeah, basically it works. For when there are keys, as very often keyboard keys are used in the programs, What we do at the moment is that we transpose them into new objects which just have the look, the costume of exactly the key like it is on the keyboard, and add that as a touchable object somewhere on the screen, not always the best position, but what then happens is that this is just a normal object. When touched, it broadcasts a message, and instead of the when key so-and-so is pressed in the Scratch program, we replace that with a broadcast message to exactly the same place. Yeah? And then kids can, of course, decide, okay, I want actually to replace that with some inclination sensor or whatever. So I think I'm at the end of my time. Thank you very much. I have stickers here, and I'll be available tomorrow and today, and also I have a poster tomorrow, so ask me anytime, but I should give time and place to you now. Thank you very much again. Thank you.
Thank you very much, Wolfgang. Thank you very much. I think Eckhart needs to plug in some cables, but then he will be ready for the next presentation about building your own blocks. And I'm very interested in it, so I hope you enjoyed it also. Thank you.
Yeah, hello. I'm not so familiar talking English, and so I wrote everything on the slides here. I want to tell you something about the context of computer science in German schools and the consequences of the situation. The situation is not so great. And then I will try to check whether BYOB can fulfill the requirements. And if we have some time left, I can show some examples. In Germany, the access to higher education and universities or so can follow two ways. It's possible to visit technical or economical schools, but the normal way is to visit the German gymnasium. And gymnasium can be translated to grammar school with good reasons. It's really dominated by the languages. We take examples, the syllabi of Lower Saxony, and there we have three big fields. The field A are languages and arts, and as you can see, the portion of the lesson times is 46%. Then we have social sciences, field B, and the portion is 20%. And then we have math and sciences, computer science is part of this area. We have 27%, and then we have sports and so. And the situation in Lower Saxony is quite good. In other parts of Germany, the portion is even smaller. So that's one fact, and another is the changes in school systems. If we take the situations maybe 65, then about 5% of the students, of the pupils, visited gymnasium, and the rest other school forms. And the professions for the gymnasium pupils were lawyers, later lawyers, physicians, philosophers, teachers, and something like that. And the way of a typical engineer or technician of my age was different from this. He after leaving Realschule 3 years earlier than Gymnasium, he becomes a trainee in any profession, and if he's very good there, then he may visit a school of an Institute of Applied Sciences, and only if after this he will be an engineer, and some of them went to university, and there they are different from students which come directly from schools. They are well informed what they need and what not. They are professional in their areas, and they, yes, they are different students. Now, about 20,000, the portion of gymnasium students were about 30%, and just now we have all over Germany 50% in gymnasium. In some cities like Göttingen, we have 90% of pupils in gymnasium. And let's see to another point. About 25% of the boys and 15% of the girls have heavy problems with reading when they leave school. Of course, they are able to read, but they didn't understand what they reading. And so we have the situation that almost all candidates for future engineering or technical studies visit the grammar school, the gymnasium, without any contact to technical problems. And I think it's a goal of computer science to be representative for this area. And the results in the sector C and the natural science are largely unimportant for school access. If you have problems with sciences, you have a lot of languages, and so you can compensate this. But on the opposite, if you have problems with languages, so you have problems with 3 or 4 subjects. And so the result is children with scientific technical interests are clearly disadvantaged. So, another aspect, technical jobs are typical for social climbers. And we have a new study from Bertelsmann, and the situation in Germany didn't change a iota in the last 30 years. We have only few pupils from working class children in gymnasium. But also other children from educated parents have some problems with technical interests, because technical jobs don't have a great reputation in the social groups, and parents normally don't like this way. So they are underprivileged twice. They have problems to reach a gymnasium if they are social climbers, or there will be them. On the other hand, their interests are little appreciated. And so it's no wonder that there are significant recruitment problems in technical areas. I think in other countries it's the same, as far as I know. So, I said computer science is part of field C and is in most countries, is purely elective. In some schools we have a few hours for computer science, but I think normally it's no computer science. It's something like preparation for computer driving lives, and it was of interest for me that in other countries we have a change from computer driving lives to computer science. In Germany we have the opposite direction. So we have this change to something like media studies. In Baden-Württemberg, a big part of Germany, this change was just completed, and so the students learn something about the dangers of the internet and using computer tools, video schnitt or something like that. And I think that's a real problem because most computer science teachers are math or science teachers, had been, and they learned computer science for their own, and they don't care about the social consequences of the field. But they have had to, they should do, then science that shapes our information society, the fundamental can't be limited to the technical basis. I come to this point later. And so the traditional computer science education has helped to turn a shift from a creative, student-activated subject towards a more receptive one. I don't like this. So what follows? The most teachers in Germany didn't have graduate training in computer science. They're autodidacts. And the subject is not obligatory. You can't rely on CS knowledge on upper levels. That means that you have to do on upper levels things that should have their place in another grade. So, in grades 5 to 9, it's more user training than computer science. And it reaches only a smart part of the pupils. And the result of all this is that the intellectual claim in the upper part of gymnasium is partly pretty thin. If you have a look on the complexity of the algorithm in schools, it's nearly the same in level 5 or level 12. You have a loop, and inside the loop, if this happens, do this. If this happens, do this. If you have a roboter, if the touch sensor cries, then the motor A starts or so, and the level 12 may be you have a loop with all characters in the string, do take the codes from the first 3 characters and transforms this anyway or so. And the difference is the tool, the computer language you use. And since we use BYOB, the students, the pupils invent things from a level 12 on level 7 or 8 for their own. And we did the wrong things in level 12 till now, I think. We had the problems not with the algorithms, but with the syntax. So teaching time is too short for learning a text-based programming language thoroughly. So you can use it as standard tool. The tool itself is teaching topic. And so we have to deal with syntax problems instead of content. And the requirements we have that computer science education should be really computer science, and in big parts it's not. It should contain many active phases and reach a much wider part of pupils than today. That's essential. And it should a suitable relationship between tool knowledge with syntax and problem solving. And from the first point, it should be treated as a representative of a technical subject to get the students a chance to make experience in this field. And from the media studies, we can learn that the subject has to discuss a social and cultural context of their thematics from a subject-specific basis, not independently. So let's have a look on BYOB and Scratch. The immense success of Scratch can certainly be explained with this wonderful product, but it's also expression of despair on the success of previous tools. And it's designed for preschool or primary schools, and if this tool is successful on intermediate level or even later, it tells more about the old state than the new. And the teachers tell this. But it's accepted by the teachers, and the widespread acceptance of Scratch has to do with the fact that it's considered by the teachers as a preparatory school. It doesn't danger their professional look on themselves. I think that's an essential point. And we may look on BYOB. We have two different reactions. On the one hand, the reaction is almost euphoric, of course. On the other hand, teachers were offended. And that's in the first time, they were very angry when they saw BYOB. And what's the reason? I think a difference to BYOB is, to Scratch is, that BYOB affects the core area of expertise of CS teachers. And they are mostly self-taught. And that means the biggest part of their profession is programming, and normally programming in a special language, let's say Java. And if Java, we don't Java, it's dangerous for them. And the question, which educational purpose dealing with syntax errors has, wasn't turned out in the past. And I think it is not answered, because this questions doesn't exist in the part. I think there's no. Let's have a look to the students, and they don't be all enthusiastic. The majority was easily cope with it. They have no problems with BYOB, but the working program did not match to their image of computer science. And we deal, normally if I have new students, I make them two pictures of what's that? Philologe. Ein Philologe? Ja, ein Germanist. Yeah. Yeah. Literature? Classical literature, yeah. Greek, Latin. This one. And on the other hand, a computer scientist. And the pictures are all the same. The Greek teacher sits in an old chair and reads in a book. He's reading, he's not writing. Never he's writing. He's always reading. And the computer scientist sits before his screen, and on the screen are strange symbols. Most he's angry. He's very angry, and had some problems with the characters on his screen. So, a computer scientist has to match the image from a computer scientist. And because a lot of the little ones want to be real computer scientists, and if they're doing something that doesn't match this image, they have a problem. And if you have understandable symbols on the screen, you aren't computer sciences, and that's a reaction. And a real problem, I think, with BYOB is the appearance of the inherited from Scratch. Scratch is a tool made for small children. And some of the older students don't like it too much. If they are really great, it doesn't matter. So let's have a look to BYOB. Computer science has to be really computer science in schools. And there is a good situation. The concepts of scheme helps us immensely. With the MIT, we have an elephant of competence on the back. And we have no discussion whether a tool made for kids, maybe, from the surface here, is sufficient for upper-level school courses. Active phases, I think it's not necessary to discuss this. The visualization capabilities are great, really great, and special debug processes are normally unnecessary. Debugging is part of the program. And because we can see any errors, and I think we know all this from old Logo turtle graphic approach, which did the same. It's completely different for kids if they know the error and correct it in the code from finding errors by analyzing the code. We have some experience now towards release with BYOB, and I think that we will reach a much wider part of pupils. In a lot of schools this happens. And it's another effect. I think almost in the beginning, almost all students felt that the real programmers, the real computer scientists are the Java ones. And BYOB is for us. But in the meantime, they have much better results in tests, also in final tests, the first. And the reaction, meanwhile, in some schools is other. They say, Java user, try first to get our results, and we can discuss about programming languages. Yes, I have some time problems. I think that's clear. I think one of the arguments for computer science in school is a technical aspect. And computer science is a technical subject. If we do real computer science, we have this aspect. And the definition of techniques normally isn't soldering or filing, but purpose-oriented problem solving. And that's exactly what we're doing. And here, the interactive features from BYOB that they get from Scratch are important. I can use PicoBoard, Lego sensors, actuators, and so with the different tools, and they are not necessary. It doesn't belong to the core of BYOB, but they are very helpful and motivating, also for older kids. Now we have a difficult point. In the social and cultural context, if I think it's important for computer science in schools that it can show that we can discuss from social problems from subject-specific with subject-specific arguments. In the past, normally computer science teachers stopped the lessons and then they read the Privacy Act or something like that. And because it's difficult for them to teach the other aspects. Let's look what we can do. One project was Computer Science Helps, and we went into different systems. We took a supermarket, bank, gym, and so it was. And the little ones, you see one, interviewed the employees, take notes, photos, and takes some time, and then they're experts for the systems, for the supermarket, and then they realized parts of the systems. For instance, a checkout scanner, RFID, wardrobe, or something like that. And they realized it's maybe with Lego, and you see the little aspect that I think he will vanish soon in the box. And it was very nice to see this. Another project were networks. We can realize some computers with the mesh features from BYOB and implement simple functionality like a chat program that are 2 or 3 blocks, not more. And we can discuss interception here, and we try to do something. Ganses with simple encryption. Caesar Visionaire encryption they invent for their own. And then we discuss communications with bank, ATMs or so, and customs, and we can try to implement that. Fiberglass was very nice. It was grade 10, and there the groups are new composed. So I put some parts of a globus from the Earth, mix them, and if you have success in any point, you can you get some of these cards, and then you have to change 3 times California against Congo, and so, and they have to find also students from other parts and build their own globes. Fiberglass, we can simulate it with Pico boards and Lego lamps and Scratch for Arduino. It's very simple, but you have to invent protocols to transport any information. And then again, you have the problems in the systems. So, and the filing cabinets, we have something N. I have a picture from down. It's a IT officer manages a cloud, and the access to the data can't be realized with a mesh functionality. I find a mesh is great. It's so simple, it's so really great. And we again have passwords and so on. And the last, here are the borders of this way. Social networks, I tried with grade 12. And we only modeled this system with UML and tried to build a system that has all necessary features but can't read any data or images or something like that. And after some discussion, We realized this with asymmetric key management and encryption, and it was very simple to do this. And the question arises, what kind of payment is used to finance such a system, money or personal data? It's very simple. And it was astonishing for me and the students that they can realize this. It's no problem. But we didn't find any results about the social or psychological consequences of social networks, and they are in another field. And here maybe are the limitations of this way. If we try to find a technical approach to the consequences of computer science systems, I think we only can find answers if the consequences are in the area of computer science or neighbors this. And if they are in complete other fields, I can't deliver contribution to this. And maybe the experiential educational access has its... that's